I hope the volume is on so we can go ahead. So this is our basically last lecture. Next Monday will be our review section together with the reviewing the past paper exam. So that will be our last lecture, and also last time we're here. Next Thursday, no class. You directly go to the exam at night. Okay. And tonight also we have a tutorial section for you. So just to remind you that if you have time, you're really welcome to join the YIA. Oh, I see. It's not coming out yet. One. Sorry for I didn't notice that happen. So it will be in YIA 405. So if you have question, please feel free to go, or if you don't, just please email the TA so that he can talk about those parts. So it's YIA 405 here. And then we'll have that. And then if in the case that you know you're going to miss the exam for legitimate reason, please email us, and then we will do make up for those who have legitimate reason. So either you're sick or you have a conflict, and then we have figured out. If we don't know, you don't no reason to miss your exam, then we can't really give you a makeup. Okay, unless you have a strong reason so that we can give you a makeup. Otherwise, we only offer makeup for those who have a legitimate reason. Okay, so our very last class will be finishing up the very last few slides, especially on the prediction and confidence level for your model. Okay, but before we do that, let us review the whole thing, because I think that would be make sure that, because we're not in a hurry, just a few slides left. So, but just make sure everything is all right. So regression, just to recall, you're trying to have two numeric variable and try to build up how they're related. Okay, so it's like education and income, they're all numbers, and you want to understand how the numbers are related. Okay, and to do so, you must have the two number measured for the same individual, right? X1, Y1 of X and Yn, and the idea is to draw a line that's called simple linear regression, right? Simple is only X to explain Y, not more than one X, and linear because I try to build up a linear related idea. Okay, so basically just this line, right? We try to draw a line and to present the data, right? So basically a two row is like you try to collapse the a lot of data into a line. Okay, and this must simplify the model, because before you have a lot of data, but you now collapse the data into a single line, can be represented by two number, which is the intercept and slope. And also we also extend what we know, because the data only have finite number of points, but the line is actually infinite number of points. So basically two things: simplify and extend. Okay. And the method used is to call the least square method, is the minimizing the sum of the vertical distance. And this is what you know from the later stage, is minimizing what? SSE. Okay, sum of square errors. Okay, this is different. This is minimizing error. But of course, sum of square error doesn't mean a lot in this model, because at the moment there's no statistics. So there's no error by construction, but the vertical distance is error if we adopt the idea have later, right? So we minimize the sum of vertical distance. And the reason we want to work on vertical, not horizontal and perpendicular, is because we want to use X to explain Y. Okay, so that's the reason why the problem we don't fit the model is the vertical, not horizontal, because we use X to predict Y. If you use Y to predict X, then the horizontal. Okay, if you don't want to predict anything, just the best fit, no explanation, then would perpendicular, right? So that would be what we want. And if you are minimizing the sum of the vertical distance square, then the line, the best fit, will pass through the center of data, represented by this A equal to Y bar minus BX bar. And the B will be just simply related to direct proportional to our covariance of XY, and inverse with the X, variant of X. Okay. So we explain by graph how this thing, I'm not going to repeat because I think we did it last time already. So that is give us a two formula, and then we show you how you can calculate that in Excel with the slope and the intercept. So that is done. And after that, we're trying to go into a model because statistics, right? You need to figure out random variable, right? So far we have no probability, there's nothing. So why we cover this, right? Because it can be covered in math class, right? So the thing is, like, we know there's some always there are thing that is not in the model. Either there's something you cannot measure everything, right? If you measure everything, then your model is perfect, right? Because in the world, there's not everything you can measure, right? In this case, y is determined by x, but also something not in x is epsilon. Epsilon is something you can't measure. Say the example that y is income and x is education. There's many things that determine your income other than your education, like how your personality is, how your luck is, how GPA you're doing, right? Besides the education, right? GPA is important to depend income, right? And but GPA, of course, you can, in this case, in this model, is random for individual, for each income level, that individual random. So we assume the x are non-random, which is there's not random variable, right? But the epsilon are random variable. But if epsilon is random variable, y is also random variable. Okay, so x is fixed, it's not random, but y will be random because of epsilon is random. And this random factor, which is something we can't measure, like GPA, your luck, your interview performance, or whatever, so on and so forth, have mean zero, same variance, and different individual will have zero correlation. Okay, so that is what 3 and 4 means. Under this classical assumption, okay, and particularly the first one is most important because it tells us how x and y are generated. But if we're happy to assume this, our A and B defined by least square method has a nice property, which is unbiased estimator and also efficient to some extent. Okay? So that's called the best linear unbiased estimate. Okay? And after that, we know the interpretation. And after that, then we have one thing to add to the model because once we assume there's a model by epsilon, then we can have something to do because there's a new parameter sigma square introduced to the model. And this sigma square is important in the sense first is it tells us how good the model is. If sigma square is big, then your model is not as good as you want to be. And second is the sigma square, which is describing the random variable, the only random variable in this model, but besides y, will determine the sampling property of A and B, right? Because alpha and beta are just number, but remember A and B are random variable, depends on the sample you draw, right? And that means that by knowing the sigma square, we know the sampling property of A and B, and we can do inference like hypothesis testing and interval estimator or common interval for A and B, right? So to do so, we basically do the sample counterpart is called EI residual, right? That is like this. Okay, in case you oh, sorry, I didn't share my screen. Sorry. In case you don't see this part, right? Probably you would able to recall what we learned last time, right? So we have this x and y, right? And we assume x and y are related by underlying is an alpha here, the beta here, right? So this is y equal to alpha plus beta x, okay? But we assume that this is not the end of the story because beside x, there's a random factor epsilon, right? That's something that's outside your model can determine your y. So that's basically even if I give you a fixed x, okay, then you will not only observe this number, but it will be somewhere above, somewhere below, right? It depends on what kind of epsilon is, right? Maybe this value is the guy who has higher GPA, and this guy is not, right? Or this guy is someone who have bought that spot and this one not so. Okay. And the variance of this is sigma square, right? And these are all the numbers are referred to the error, right? This error. There's no I, this error, right? And depend on data we get, right? Maybe this data we got is something like this. Sometimes it's in the line, sometimes not, right? But when you try to fit this regression, you will basically fit something like this, maybe, right? And if you fit this regression, this will be your A, and the slope will be your B. Of course, A and B will be different from alpha and beta in general. But on average, if you do this many times, average of this A will give you alpha, average of this B will give you beta. That's what unbiased means. Okay? And of course, what we want to know is this sigma. We don't know it, but we can do it by estimation, by estimating these guys, right? This we call the E, sorry, I made a mistake, but these are called epsilon, sorry. This is epsilon, these are error, but our residuals are actually these are residual E, okay? And our E is very similar to epsilon, right? But E is based on the line you drawn, because you never know the red or the orange thing, right? Because you can only estimate the green. Turn out that if you use the you calculate the standard deviation for the E, right? This E, sorry, which is right, and this is our S square. Okay, this is the standard deviation based on your regression error, right? And why n-2? Because you estimate two things, the A and B, so you estimate two parameter. So that's why you would have to -2. Okay, and that's why if you have more variable to guess, then you have minus more. But that is why you have the -2 here. But this S square is a good guess for sigma. Okay. And very often, if you look at subsequent classes, right? This is, as we said, this is SSE, right? And the whole thing is called MSE. Okay. And the S, which is square root of S square or square of this guy. Okay. And this is called RMSE, root mean square error. Okay. But just the name, it's not need my class, but just put it there in case of those of you who learn machine learning, they will see that very often. Okay. So once we know this, then once we have the guess of sigma square, then we can do hypothesizing and interval estimate for the B, because A and B are random variable related to sigma square. Okay. And if you're willing to assume that these sigmas are, this epsilon follow normal distribution, A and B also follow normal distribution. Okay. And we know that if I know something is normal, I can do the standard hypothesizing, right? Just one sample test. I know something is normal, I can test whether they're 0 or not and draw an interval estimate. Okay? So that's what we have done in the last class, right? If you're willing to assume, okay, it's normal, we know the A is also for the bell curve, right? If the error bell curve, your A is also the bell curve, okay? And once the bell curve, I don't know sigma, but I replace by S, I can use the t-test, okay? And also we can use the interval estimate for T, okay? Similarly for B, you can do the same. If you're willing to assume that, that is, we have to do that B as well, and this interval estimate. Okay? In the case that you don't fully remember, this is our Excel table. You need to know very well if think that is the most important in this chapter, right? Look at the B's and these are all the coefficient, right? This is the A, right? And this is the B, and this is SA, right? And this is SB, right? And this is the column D divided by column E, right? This is the same. Okay. And this is the p-value of two-tailed test, and testing whether A or B are zero. And in that case, they don't pass the test. Okay. So we can't reject H null. So this regression is more or less useless, right? Because you can't tell A is different from zero or not. Okay. So that's why we don't really like it, because these are include zero. So basically, this regression is basically, we would not take it seriously. Okay. And that's why when you run regression, you always want to make sure that the thing you're interested in, either you want to reject or not, but of course, sometimes you actually want not to reject, right? Because you want to say suppose Y is income, X may be gender, right? You don't want the gender to affect, right? Or sometimes you actually don't want that to happen. Sometimes you want, but anyway, that is the key idea. You want to see whether the beta is useful or not, right? In most cases, in business, we want to establish they're related. Okay, so we really want to reject, and these are confidence level, as we said already. Okay, and this we covered last time. And the very last thing we covered last time is called the coefficient of determination, which is R squared. It's how much we explain by the regression, right? Just remember, look at this picture. Okay? The thing that we want to explain is things that we want to explain this part, right? Because even without X, we can predict Y by Y bar, right? So what we want is to explain why Y is different from Y bar, right? Which is our SST. And your model give you this number, right? So this is the part explained by you that is called SSR, right? If you look at the notation, right? This is the Y hat minus Y bar, right? And this guy will be sum of the Y minus Y bar squared. Okay. And what is this is SSE, as I mentioned. You always minimize this, right? This, right? This is the one that the regression, Z squared, always do is to make sure that SSE is as small as possible. Okay. So that's why when you try to look at how good the regression is looking at the SST over, so SSR over SST, right? Because you're minimizing this guy, so you just maximizing R squared. Right? That's why actually regression we're doing is maximizing R squared. Right? Because SST is fixed, different data. You can't do anything by anything, right? That's SST is calculated without any model, right? So SSR and SSC is determined how good is your regression, right? The better the model, better fit. Okay, this must be between 0 to 1. Okay, and some of you ask me, okay, what is the SST and SSR in your data is here? Okay, so by construction, your SST is here. So SST. Okay, and SSR is here. But your SSE is here. Okay, but you will ask, if that's the case, why I have to say SST equal to SSE plus SSR? Oh, that's a math result. Okay, but this must be true. Although in this particular case, the distance is smaller. But remember, you sum of the square all of them. So this must be true. Okay, and that you guarantee this one. Okay, so you would ask, but you don't worry about that. The proof is already in the slide. So if you would really want to know, you can check the proof, or it's easy to put my slide on the AI. They will explain. Okay, if you don't really get my proof, but that is well established there. Okay. Okay. Same if the number is here, right? Then the SST is this guy. Okay, this is SSR and this is SSE. That's no problem. Okay. There's no problem. Okay. But in general, no problem. Okay, so don't worry about that. There's a math, but I just pick a particular point to illustrate why they're kind of related. But remember, this is distant. We're not a square yet. Okay, so but saying that if you do this square for everything and this square everything, that add up will be SST. Okay, I'm not saying that distance is SST, but this distance is this guy. But you take square, add all up, will be SST. Okay, just to make sure that you don't confuse this. I don't confuse you with this diagram. And the next thing is because we have SSE and SSR, we can do the same. Okay, you can same idea. You can calculate variance based on the SSR and SSE. Okay, and turn out that you can also why this is a two-way to do it. Actually, this is if you look at ANOVA, okay, this is actually C-1. You have two group, okay, you have two things there, okay, and you calculate variance of between these two groups. Okay, it's group of this and group of that. Okay, so you have two group there, and you this minus this is basically the way to do is slightly different, but the math they can show that this SSR has a chi-square distribution of 1, and SSE is actually chi-square n-2. There's some math showing that, and that's why you can compare this in the F test, and this F test, okay, will give you to check whether beta equals 0 or not. Okay, so why? Because if you can imagine if MSR is very large, okay, what does that mean? SSR is very large compared to SSE, so your regression will be useful, right? If SSR is not different from 0, say for example, it's not different from SSE, right? Then your regression is basically useless, right? Because if they're the same, okay, if the line is like this, right? The measurement FSR and SSE the same, right? Because SSE is actually capturing what? It's basically is epsilon, right? Because this is SSE is what? The MSE. The MSE is capturing what? Sigma square, right? And this guy, if there is a thing to explain, is sigma square plus something, right? Because beside the variance, but you also have thing explained by there, right? Coming from beta, right? There's something with the beta. So that's why if SSR is, or MSR should be MSR, right? MSR is much larger than SSE, then your beta will be not 0, right? If beta is 0, then they're the same thing, right? If this flat, right? The MSR will be measured same as MSE. So that's why it's testing beta equals 0, right? Beta equals 0, this is simply just sigma square related, and this is also sigma square. So their variance should be the same, right? So that is the idea why this F test, we have MSR bigger than MSE, and it's testing beta, okay? And also, if you look at the Excel, you will see this p-value exactly same as this p-value. Same thing. Because why? They are both testing whether beta equals 0 or not. Okay. One is a t-test, one is an f-test. Okay. And if you are careful, you will see this. This called t, this called f. You can check that f equal to t squared. This is relation. And I explained that in the technical slide, but this is the result there, okay? That you can easily check they're related. Okay. And just to remind you, okay, this is R square. Okay. And this is what SSR, this is SSE, and this is SST, and this is what? This is SSR, MSR, which is SSR over 1, and this is what? This is MSE, this is SSE divided by n minus 2. Okay. In this case, n is 5. Okay. So divided by 3, which this is n minus 2. This is 3. It's n minus 2. Okay. So column F is scattered by column E divided by column D. Okay. This column F here, right, is column E divided by column D. Okay. So 4.9 divided by 1, you get 4.9. 13.1 divided by 3, you get 4.33. Okay. And what is F? F is just MSR over MSE, right? As I said, MSR will contain more than sigma square if beta not 0, right? If beta 0, MSR and MSE should be same, right? Because they're also capturing the only if MSR is 0, right? It's no explained by the data, right? So the MSR is just capturing the variation of the data, right? Why you should not have any slope, right? But the slope may exist because of variation of the epsilon, right? So that one actually capturing the variation. But MSC is actually capturing what we said, right? So they should be the same if beta equals 0, but if not, they were much bigger. So it's a right tail test here. Okay. So that means that this p value, just to remind you, will be the f1 minus f this 1.122, okay, and will be 1.3. I forgot true. Okay, because it's a right hand side, it's a right tail test. You don't multiply by 2, right? Just this number, right? Because that is here, right? 1.123, right? You just calculate the error of this guy. Right tail test, right? Why right tail? Because this ratio, right, should be very close to 1, right? But now you are checking if beta is not 0, then MSR must be much bigger than MSE, right? So that's why the right tail. So you just try to check this area. And this area is F13, right? This F13 here. Okay. So we want to check if this is large enough, okay, to reject. Okay. So this is done with this line, right? This is done with all the Excel. Okay. We only left with something very simple, so don't worry. But I already covered the most important slide, which is this slide, which I expect you to know how to do it. Okay. If you check some of the past paper, which you may ask, the previous cohort, I actually asked question in this one. Okay. Like the ANOVA, I just blank out something, ask you how to fill up the thing, same question. Okay. But you may be prepared to how to handle that, right? But that would be something I ask, right? I'm not interested in asking you how to calculate the number in the Excel, right, directly from the data. Rather, I want you to see if you can look at this and draw conclusion, right? For example, I don't give you this t-stat, right? Probably you can calculate by dividing D to E, right? If I don't give you the column G, then you can also tell me the Excel formula to calculate this number, right? And similarly, you can also calculate this. I give you enough data, right? I take out this number, you can calculate that. Same as F. If I take out anything, you can able to calculate that, right? At least you can tell me the Excel function to calculate those. Okay, this is something I want you to know because that is important, right? And maybe I took the p-value, you can tell me whether you reject alpha equal to 0 or not equal to 0, right? What is the interval estimate for our alpha and beta, right? 95% will be here and here, right? So that would be the thing I have been asking. Okay, is that okay? So how to use this Excel output is important, right? How to understand how they're related, and that's why I'm asked, right? I'm not interested in, hey, how can you come up with 3.9, 0.07? I'm not that interested in because no one actually ever calculated, right? I mean, you rely on computer, right? Just need to know what are they, how they're related, then that's I'm happy. Okay, how to use that. Is that okay? I'm not interested in pure calculation, right? I'm not interested in, hey, how can you calculate R square? No, right? Maybe I give you, in this number, you can tell me how to calculate R square, right? R square is 4.9 over 18, right? Say this R square is SSR of SST, right? So you can calculate that, right? Is this Excel function will be E12 divided by E14, right? So that's what I'm asking. Is that okay? So this is the most important thing I would want to convey to you, because if I ever ask regression, which may or may not, this will be the slide I'm focusing on. But if you understand this slide, then basically you understand everything in the class so far. All right. So there's nothing. Also, this is also we said about that. This is S, right? This is S, right? So, okay. Is there any question before I proceed? Okay, because so far we have covered. I want to make sure that everyone's on the same page because the remaining is rather simple. Okay. So we only have actually one slide or two few slides, so don't worry. Okay. So once now we are happy, we have considered case, we have run this regression, okay, and check out that A is not 0, B is not 0, then we're happy, right? Suppose our P value is so small, less than 5%, the regression is not useful, right? Now we're happy, right? Not yet, right? Because now, remember what we've done is we have the data, right? X and Y, and we're happy that we draw the line there. We estimate A and B, and with the Excel thing, we figure out A and B we are going to say, we test the X now, alpha equals 0, and X now, beta equals 0, then we're going to reject them, right? We're happy, this model, we're done, right? So we have a model now, we have a model Y hat equal to A plus B, X. We're happy to say this is a good model, and we say when X increased by 1, B on average Y increased by B, and when X is 0, on average, Y is equal to A, that we're happy to do, right? Now the model. But that's not done yet, right? Because this model is only a point estimate, right? So remember, Y can be more than this, right? Because depend on random term, right? This Y headline is the average performance of Y, right? So it really depends on what you remember here. Our Y is just average, right? It depends on the E. It can up and down, can be a lot of numbers. Okay. Same here. This line is just average value of Y. Okay. But how good it is, right? Can we talk about more? Okay. Can we talk about more? Okay. Can we say more about, since we have estimation of this guy, right, by our S square, okay? So can we get a confidence interval for the prediction, right? Because remember this line, what it is I give you X, you go to this line, this is my Y, okay? y hat, right? It's y xi is y hat, right? This is coming from this line. But this is only point estimate, right? Can we get interval estimate? Okay. Say, for example, can we get 95% confidence interval? Okay. Is it going to tell us what is the value, right? I'm interested in not only the point estimate, I want to know on average what are they. Okay. This is exactly you see in the typhoon, right? The observatory not give you 1 point only. They give the area. Okay. Remember, this is the model. You can imagine the supercomputer, right? Telling you where the typhoon they are, right? It just not give the observatory not give you 1 point, but telling you that how likely are all other values. Same idea here. Okay. This line can give you, say, if you get 10 years in schooling, maybe 10 years in school, okay, maybe the salary you get maybe 20K, right? But this is only average. We want to know how 95% where they are, right? Same as the typhoon, remember, right? In the observatory, right? There's a map there. Sorry, map here. There's a Hong Kong is here, right? There's a Philippines, sorry, but this somewhere Japan, right? Then you see the typhoon, they will say, oh, the typhoon is something like this. Okay. And they not only give you this, they will give you a confidence interval, something like this. Right? And say this is a where likely the typhoon is. Okay. And you see the further away the range is larger. Okay. You expect to see the same actually in this confidence interval. Okay. What you will see usually will be like this. Let me draw a picture. And then with a break. Okay. So what you will do is you have a line, okay, based on data you draw. Okay. And suppose this is your X bar. Okay. This is your mean estimation, but the interval will be something like this. Okay. When it's near X bar, the CI is very narrow. It's narrow here. When you are away, much wider. Okay. It's wider here. Why? This is the same as the idea as this, right? When you're closer, when you're very early, you have more confidence. But when you're later, when you're further away in the time, you get less information. So same as here. When it is near the mean of X, we have good idea what's going on. When you're further away, you are less sure. So the CI look like this if you try to plot it. Okay, but we'll talk about that. You will see why this is the case. When we look at the equation, you will see the variance is proportional to the number you get is further away from the X bar, much larger. Okay, we'll talk about this equation as I hint here after the break. Okay, let's a break of 15 minutes. And in the meantime, let's do you reply. It's 2:18, so we'll resume at 2:33. Okay. And since this is our last class and also our last class, we also still have class, last lecture. Last class is next class will be tutorial. Our last real class, and our last time we use this classroom, we're celebrating with my snacks. So I go over to hand out the snacks as our celebration. Of course, also for me. After this, I don't know when. Hopefully get more. Celebrate. One more time. Don't be how rather than how. But what I line rather use. It's the game you know how.
I don't know. I would not be. Come on. Explain.
Question? Like, part of it.
Oh, yeah.
You say email. Or the question you have. You send it to them back. Like, voice notes, you know, they're not getting it. And also, next Monday, we go Q&A and also task. Which is really fun. Okay.
Such a yeah, as long as we treat the just say like what to the relationship part of this. And then actually like we're having a part of the relationship and like actually like supply and demand. What? And then they're like, I'm like, but you're still like what is the
So let's see our probably last U reply for the class. I mean, next class probably you still do U reply, but probably just for raising question. Do we need to draw graph in fun exam? I don't know need a graph, but for my past paper, I never asked for graph. I can't say whether I need or not, but in the past I never asked. So the probability of asking is so low that probably can ignore. But I'm not sure what graph exactly in your head. But I never asked, so probably the answer is no. But because I don't know what the graph in your head, in your mind. I mean, there's no. I don't think there's anything that the graph in my class is just to explain what's going on there. You don't have to draw a graph, right? But you still probably say when the hypothesis testing, you have to say the hypothesis, right? The graph is just for you to understand, right? So it's nothing is required from that. How do you look at this? You will be given, okay? As I talked to TA, actually we'll give you the T values. I think if the T value required to do what we give you, okay? For the F, you have to, if we do F, then you have to write the Excel formula because F will be too much to give you in the table. So I think for the T test, you should not be worried too much about the table. Of course, you should bring as well, but I don't think you worry too much about T table. I will give you, okay? Unless I ask you to do the P value, then you do it. But T, I think I give you, okay? You should be able to figure out from the question, okay? The question will give you the T value that you need for you to do the calculation. I hope I answer your question. If not, ease your concern, because this time it's very good. The TA tell me that I should give you T value. Usually I don't give, but in the upcoming exam, actually T value will be given if I ask you. But F, you still have to write down the Excel formula because you can't redo it. So we just write down Excel formula. You tell me after the Excel formula, the value, how you do the decision. Actually, it's easier, right? If you don't have to do any calculation, that's easy. Just tell me this formula, the p-value based on this f, tell me whether it's more than 5%, less than 5%, then you reject or not, right? So it's actually even easier if I don't give you, right? So giving you is actually, you have to do the calculation. You have to know what the way to pick, but okay. So hope to answer a question. So it's not Monday yet, right? It's Thursday, so we're not done yet. If Monday, then we're happy, but I still have my last class. Okay. This is my last dance. Weather. Okay. Unfortunately, today is very cold, but next week will be okay. Will be according to temperature forecast. The interval will be 17 to 24. Okay, so it will be normal. Okay, you don't have to too much worry about if at night is cold. Yes, regression, that's very important. Make sure that you know about regression. Okay. So the speed is okay overall, but not that bad. And I think most of you can follow, but yes, this is the first time we have 4 more than 5. Usually you have 5 more than 4, right? So today, pretty happy. But probably there's only one, say 3. But if this one go to 5, then we'll have very close. But today we have 9 compared to 5. Well, last thing, any jokes? No. Unfortunately, we don't have joke to conclude our section. But let's see if you bring a joke on Monday. We can share it with the end, I guess. Or if you don't have, if your question, bring your question. If you don't have a question, bring a joke. That would be happy, right? That would be more fun, right? If your question, bring your question. If you don't have question, just bring a joke. Then we have to, let's conclude our class, but this is the very last part. So as I mentioned, how you use the regression model is what we call the point estimate, right? The line is actually give me point estimate, right? What I said is in this graph is, right, if I give you x0, right, what is the value prediction? The y0 hat will be just a plus b x0, right? I give you any value, you times b plus a will be the prediction of y, right? So that is what I have this slide, right? This is if I give you any particular x0, the average of y is given by this one, right? But this average, right? Remember, the real one, the y is a random variable, right? So y can be anything, and right, we'll be adding, right? The real y we're adding epsilon, right? But we care about average, mean response, so that's why this is gone. Okay. And you want to see the variance of this guy, right? And turn out to be this thing. Okay. And this is actually variance of A plus variance B, right? But at some point here. But anyway, so you notice the variance of what you predict is, as we said, related to how close to our x bar, right? If x0 is same as x bar, then the variance is simply sigma square over n. It's very simple, right? If x0 is equal to x bar, this is 0, right? So left is this guy, the smallest. If x bar is not equal to 0, you have this term, positive, so it's bigger, right? So that is exactly what I draw here, right? The variance is actually larger when you go away from x bar. When you close, it's narrow. I don't think I draw narrow enough. Maybe you can think higher, right? Something like maybe higher in this direction. Okay, maybe something better, right? It's more wider, right? And these standard deviations like this, right? Because you just replace this by this and take a square root, right? And if you are happy to assume this normal, the whole thing is normal, right? So everything very nicely. These are point estimate. This margin of error, you just add plus minus this guy. Okay. And that's what we have. Okay. And you can, these are our very last slide of a course. Okay. Is you can do the auto calculation, right? And you plug in this, figure out what is the standard error, then you just 95%, it just put this. Right? Because this guy is just plus minus, and this is the critical value. Right? Just come with this guy. So that's all for what we are covering. Okay. And that one function we didn't talk about is RSQ cell square. Okay. So we just give me a number, we'll give you 0.0722, right? So that is this is data, right? You get this RSQ, R square. Something we didn't talk about that. Okay. And this pretty much our course. Okay, we're done. Of course, there's still time. Of course, let's do a Q&A and review. Okay. Because I guess I don't want to, as I said, the most important thing is in this set of slides, it's just this regression. Okay, if you understand this, then you are on basically. But last year I didn't ask regression. I'm not sure this year I asked, sometimes I'm rotating and over regression. So to decide whether I have a regression or not, I can't say. Okay. So for random. So it depends on whether you take the main exam or make up exam or something. I just do the randomization to see what you will get, but you will see the expected exam will be very similar to what you have seen. Some question, short question, right? One short question about everything. One question about testing estimation. Okay. Basically, question one will be first two chapters, right? And the second question will be some in the middle, and last question will be an overview questions along that line. Okay. So first I would do is to open the floor to see if any question you want to ask. Okay. And if not, then I will just review the whole everything. Try to see if anything particular you want me to cover. Okay, because we still have half an hour to go. Of course, if you are busy, you've got exam, you feel free to skip, you can go home. Have fun because last class is over. And before you go, you can pick more candy from here. But let's me start a question. You can write down what we need. I make it anonymous because we already have thing there. Just type your test here. I just try to answer it. Okay. Any question? Do you have any? You can just type here. I just immediately see your answer. Question, I just try to deal with. Okay. So just type here, then you have any question, I go over that. If you have any question on any slide, just leave it there and I go. Because I don't like to. And next class, I will do the same. Right? We'll go over the past paper. And after that, if you have time, we'll go over it. We'll do the Q&A as well. Not guess. Oh, we can do that. We'll book the computer lab. If you want to do it. I mean, maybe I'll book the server first or second, make up time pass to I'll talk about it. I'll type on slide and get enough people. Even one people come up. If no people there, I go there, no people there. I think another one or two people there. Probably one day sometime. So, or at least someone can attend by Zoom. So I think the solution is uploaded in the assignment. If not, you can email TA. I think someone already emailed TA for the markings. I think it's there. Many people ask that, I think you have but it's there. Another question, please feel free to let me know because we don't want to waste the time when it's better use for you to ask questions. Of course, if no question, I can go over my phone. That slide here with see both icon. Okay. And the question is that which type, or you can just tell me directly again. What type? No question. Of course, I can also got an over if you want to, but get over 2 and over. Maybe I just in order to make sure that we don't waste too much time here, just I set a timer, 2 minutes. No, then we will review costs. Okay. For those because not everyone will go to the tutorial. Right? So let me review the material a bit. We're starting to the end, then hopefully. But of course, if you're busy, then feel free to go because I know that you're busy. Meantime, we'll just see if you get it. Okay. Just wait. So if you don't have the question, just you review what we're covering. Done. Maybe I'll send out a question there to see. ANOVA. Okay. So let's see more questions. I go over ANOVA. And time we'll go a little bit about two-way ANOVA. Just give you the idea what's going on there. So there's a question on ANOVA. So let me answer them. So first, you don't specify which page, so I can only go very general from beginning to end. So ANOVA is what? Is to see a special case of, extend case of two sample t-tests of same variance. Okay. Two sample t-tests, same variance is compared to group. If assume the same variance, the mean the same or different, right? So just to recall, this is actually coming from a generalization of this two sample t-test same variance. Is this guy. Let me make sure that you know what we're talking about. Is in the, I think in the slide 57 for hypothesis testing, we have this guy. Okay, this guy is comparing two bell curves. Okay, I assume the population boys and girls come from the same bell curve, come from the same variance, but they possibly have different mean. I'm going to see if the same mean or not. Okay? So the question is, if I try to draw a picture, is the following. Okay, I know there are two population, right? Maybe some bunch of men here and bunch of women here, right? I want to see how willingness to pay for them, right? For the product, okay? And the idea is that we know that we assume that the boys or girls are also follow the bell curve, the underlying, okay? And the bell curve have the same variance. So this sigma girl, same as the sigma boy square, okay? They're the same. Though both are equal to sigma square. Okay, the same variance, the same shape. The only thing we want to see is if this mu B and this mu G are equal or not. Okay, so the H null with your mu B equal to mu G, or 1 and 2, right? Not equal to. It's two-tailed test. It can be more than less than, it can be. This is also okay, okay? So this is only two samples. ANOVA is talking about more than one. So it's the following. With a number line here, we have group number 1 here. We have group number 2 here. Okay? And we have group number 3 here. Okay? They have same variance, different group. We want to see, it's a normal, right? We want to see actually this group means, which is x bar 1, say. This is maybe this is mu 2. This is mu 1. And this is mu 3, right? So I don't know whether the data is like the data only with some data is coming from this distribution. We want to use data to see if the following is true. Is whether mu 1 equal to mu 2 equal to mu 3. Okay. Or not all of them equal. Okay. So that is what I see, is whether one test want to see this location of this 3 potential bell are the same location or different. Okay. The application is you are doing some growing trees or some gardening, right? Different condition, you can grow the tree and plant. You want to see different way to do it. Are they same or not? Right? Once and for all. Right? Of course, you may ask why I don't do t-test all the time. Right? I don't do t-test. Compare this to. Compare this to. Compare this to. Compare this to. You can do 3C2, right? 3 times t-test. Yes, you can do that. But imagine you have 10 or 11 or 100, this type of stuff. You can't really do that much t-test. Okay? You have to do once and for all. So that's the reason why we do this. If you have many things, then you have to do it. Okay. So that is the idea. Okay. But why this t-test become an f-test? Right? You may ask why this is the thing, right? Compare mean, why end up in analyze of value, right? Because that is crazy, right? Because compare mean, and at the end, why okay, right? Have I got mad or I got crazy? Okay? The idea is following. Okay. The idea is following. Okay. Why they become f-test? The idea is I have, as I said, suppose we have 3 different groups here. Okay. If I get the data, right? Maybe sometime I have data is here, data is here, data here, data here, right? And the average of the sample mean may be somewhere this is x bar 1, right? But of course, this is usually different from mu1 anyway, because it depends on the x bar, right? Depend on what sample you got. The same idea here, right? You got the number from this, okay? This will be the mu2, but the data you get may be somewhere here, right? Maybe somewhere here, then you get the mean of this will be x bar 2. Okay, this depends on sample you get, right? It can be anywhere, but of course, on average, x bar 2 will be near mu2. Same for this guy, right? This is why the same color. Okay, so data may be the center is mu3, okay? The data you got maybe a lot of them here, then you got x bar 3. Okay. So why comparing this sample will become compare variance? The idea is following. Okay. We can look at the mean of this sample mean. Okay. That is called the mean of this. Is called the overall ground mean. What means is you average or value. Okay, about grouping. Okay. Just calculate average of data you get. Then we can calculate variance in 2 ways. Okay. For one, we can do within group. We can calculate variance with this group, add up where is this group, where is this group. The calculation of this is what we call variance within group, right? So that is what the total is called as W within each group. To calculate this, within here, this. Okay. And this you divide it by how many of them is called MSW, right? It's called MSW. Okay. The MSW is capturing the sigma square. Okay, because looking within, right? It doesn't really rely on the fact that you know the mu's are same or not, right? It's always on construction. The way you do the MSW, right? Within each group, you calculate variance. The way you calculate is actually capturing the sigma value. Doesn't have to rely on the same or not. Okay. But you can also calculate the variance by looking at these sample mean you got. Look at the variation between them. Okay, looking at this, right? looking at how these X bar are different from overall. And this is called SSG. Okay. And this can be called to MSG. Okay. And this part will be sigma square plus some part related to how mu1, mu2, mu3. Why? If mu1, mu2, mu3 are very close, we're the same, this distance will be very close to each other, right? If mu1, mu2, mu3 are different, then the MSG will be much larger, right? Because you will have not just the variance of this sigma, but also how they're separated, right? So it's you have two things, this and how these things are different, how the mu are different, okay? And under the null, we're going to check, under null, this is gone. So we want to compare this and this, right? The F test will tell you compare variance. This variance should not be different from this one, right? So this F test is this MSG over MSW, right? So if this is 0, then they are, of course, there's no difference between these two variables, right? Because remember, F test is compare variance, right? You just get the standard deviation, the sample variance over, right? Same idea. So just look at the variance, right? If this is gone, then the same. If they have actual difference, the mu's are different, this must be larger than this one. Okay, so that's why it's a right tail test. The MSG must be bigger than MSW. Why? The MSG will be the variation within group, also the distance between mu1 and mu2, and mu2 and mu3, so on. So that's why it's how ANOVA is in theory. Okay, but I guess you are not asking theory. I guess you're asking how to look at the Excel table. That's okay. I don't think you are actually interested in the theory, but rather why, how we do that. So let's go to the table, okay? Because I don't think you're interested in the ANOVA. I mean, the theory is there, but probably you're interested in this one because we talk about this in the when we talk about the past paper. Okay. So let's look at this. We look at everything again to check whether you know or not. Okay. So this is what, as I said, this is SS within our SSG. It's asking how with different group, the group mean are different. Calculate mean of each group, okay, and each group how the variation. And remember, this part contains the sigma square, but also potentially if they're different. So it's much larger, it will be larger item. Okay. And here, SSW. Okay. And actually, if you see this, okay, may not be surprising, right? This can be bigger than this one because total variation. Okay. And this is SST. Okay. And the first formula you know is SST equal to SSW plus SSG, right? So that's why E11 plus E12 will be equal to E15, right? So that's something you know already, right? Variation, right? Why it's true? Because for each observation, look at the 12, 13, 15, sorry. Yeah, sorry for my misread. Okay. Right. So you may ask why this is true. One interpretation is the following. So SST is look at any data, suppose it's any data. From here, you go to here, that is SST. You go from here to the central, okay? But we are in Sartine, right? 6K Sartine, so you can look at how our self go to the Sartine. Okay, go to the mean. This is called you calculate this. This will be SSW, okay? And this is SS. Okay. So that's why add up the same. Okay. The next thing we have already here, sorry, I somehow cleaned that up, but this is right, SS G, this is SSW, this is SST. Okay. And the degree of freedom, this is what this is N minus 1, and this is what this is C minus 1, because how many group there minus 1 is standard way to calculate variance. M minus 1. How many group there minus 1? 3 groups, but you fix the grand mean, so that's why C minus 1, right? You have 3 group here, C is 3. And this is what this is, N minus C, right? N is what? N is 12 because 3 times 4, right? And what is this guy? This guy is MSG, which is SSG divided by C minus 1. So that is G12. Sorry, this is E12 divided by F12, right? So this is what? MSW, that is SSW divided by M minus C. Okay? And finally, as I said, this F test, this F will be MSG over MSW, right? MSG will be much larger than MSW, because MSW is just within group just calculated sigma square. But MSG potentially is more than sigma square, but also how they're located at different locations, right? Because they're located differently, they will be included in MSG. Okay. And because it's right tail test, this number is what? This number is just 1 minus F, this 2.3, 4, 2, 9. Okay. 2 come from here, 9 come from here, 2.34 come from H12. Okay. And 1 minus because it's a right tail test. Okay. And F critical will be just the right tail test. So it's just F inverse 0.95. This is Excel will give you 5% critical value. Okay. And then 2.9. And that's it. So you know very much everything there. So of course we'll talk about the past paper next week. We'll go over that. Right. It's good to try at home during the weekend to see how. Is it okay? I hope this very clear what we try to do it at home. And then you were doing quite a lot. Okay. And the weekend we also released optional assignment solution. Already done. I don't think we have released that, but if not, I'll release that as well. Okay. Any question you can ask, feel free. We still have 7 minutes to go. Of course, if you want to go ahead, go ahead. But please let me know if any question you want to ask. So basically, this is the table that I keep asking, but not every year how much I talk about it, there will be some students there, especially those who are watching. You're here, basically you're getting majority of your tasks. That's why even something I do very similar every year is to okay, I don't need to, so that I don't need to invent your question. Even the same question, you still can eventually put as close as possible. No people actually want. And exactly that at least try to start. Just understand what we care about. That's okay. You're here to ask a question. That's okay. Some make sure that you know. Any more question? We need to raise it because not that you get this book. I have nothing more to say. If you have nothing more to ask, nothing more to say. Because I want you to do the past paper during the weekend before you come to the class. Please try to do that. At least look at what is the question, or you can work with your friend. Get at least try to look at your friend's answer to see if you understand that. Any more questions? If not, you can feel free to go because I overrun many times in the past, so I compensate all the overrun. Okay, by letting you go 5 minutes earlier. So don't complain. I'm overrun. Okay, I compensate today for 5 minutes earlier. Thank you. Don't celebrate. If you want more, please help yourself. Okay. Have a nice weekend. Yes. You made it. Oh, you know the then you know. Is other class? Is it from not my class, right? Because I think we delayed it, our project submission date to 8th of December. 10 more days, please. So you can have more time to have fun. Really fast. Okay. Remember to overwork your project. You don't get placement. Okay. So don't overwork. Let's work out as much as we can. Okay. But don't overwork. I'll see you. Bye bye. Have a nice weekend. Stay warm. Please feel free to take if it help you stay awake.
So,
No.
only one.
Only one way of.